Well, welcome everyone. We are very happy to have Matti Jarvinen with us, and he agreed to talk about the recent findings of holography with regard to neutron stars. So we are very happy to have you, and just please go ahead. The screen is yours.
Thank you. So as advertised, I will give an review or overview talk, very biased one on the recent developments on applying gauge gravity duality to neutron stars. So the outline of the talk is as follows. I will start with a lengthy introduction, motivation, and overview to QCD and neutron stars. And then after that, I will switch to holography. I will first talk mostly about how to implement dense holographic quark matter in gauge gravity duality. And then the next topic will be then adding holographic nuclear matter in the picture and constructing this what I will call hybrid equations of state. I will tell you what they are. And then the fourth and maybe most important part will be the applications to neutron stars. So I will discuss predictions for properties of isolated, either static or spinning neutron stars, and also applications to neutron star mergers. But anyways, I will start with the introduction. And starting from the very basics, the QCD phase diagrams, which I'm sketching here as a function of the baryon chemical potential and the temperature. And well, you see that there's various phases here, and what I will be mostly interested in this talk is the part at high densities, so in this region. And in this region, the main important phases are the nuclear matter phase, which is the dense liquid or strongly interacting liquid of protons and neutrons. The density of the liquid is larger than or equal to the density of heavy atomic nuclei. And the quark matter, which is actually even more dense phase of densely packed, mostly quarks, deconfined quarks and gluons. And well, this, of course, people have been trying to explore this phase diagram in the laboratory, but the experiments are challenging in particular because the characteristics temperature scale is very high. And so there is already some results from heavy ion collisions, mostly in the low density regime, but more recently there is an ongoing effort and also future experiments which will try to push these experimental results to a higher density and also maybe see signs of this nuclear matter to quark matter phase transition, which at the moment is just I mean, it's not known if it's there. But apart from this experimental effort, there is of course lots of theoretical efforts of exploring the phase diagram, which I will now discuss in a bit more detail. Well, first of all, there is lattice QCD result. But unfortunately, due to this famous sign problem, lattice QCD results are available only at zero chemical potential or at best at small values of chemical potential, so in this green region. And another useful tool is effective field theory of hadrons, so like nucleons and mesons in QCD. And this covers the region of small densities, the blue region in the phase diagram. And the third basic tool is from first principles is perturbative QCD, but perturbative QCD only works at asymptotically high densities and temperatures. And therefore, there is this intermediate white region where basically no first principles theoretical tools are available. And so even the phase structure in this region is unknown. And this region is interesting not only academically, well, there is this experimental effort which perhaps will give us information first in this region, but it's also known that the neutron star core densities are in the region of low temperatures and very high densities, close to the possible nuclear to quark matter phase transition. And this means that, well, it's important to improve the theoretical predictions in order to describe the neutron stars, but also, like the other way around, there is lots of incoming experimental data from neutron star measurements which will constrain the phase diagram and basic properties of matter, such as the equation of state. And this brings me to the basic introduction to neutron stars from QCD perspective. So from QCD perspective, you see that neutron stars are blobs of extremely dense cold QCD matter. Well, they are quite, actually the temperatures are quite high, but still compared to QCD scale, they can be essentially taken to be zero temperature objects. And first of all, there is the Tolman-Oppenheimer-Volkoff equations, which just describe a non-rotating neutron star. So the general relativity generalization of hydrostatic equilibrium. And well, these equations map the equation of state of QCD matter to a mass radius relation of neutron star. This is the basic property. So this means two things. Well, first of all, because there is lots of uncertainty in the equation of state, we cannot really completely disentangle the structure of the neutron star. In particular, even the composition of the inner core of the neutron star is still unknown. But on the other hand, this also means that the equation of state can be constrained by measuring the masses and radii of neutron stars. So if you know the mass radius relation, you can invert these equations and get the equation of state. And for the neutron star masses, there are already dozens of results using various methods. And the most constraining masses are those where which have the highest, where the most constraining measurements are those which measure the highest masses for neutron stars. Actually, in this plot which I saw on the right hand side, this is a collection of these mass measurements. And there are some data points here which have very small error bars, and they are around 2 times the solar mass. And this means that, so these are exactly these Sapir delay measurements of neutron star white dwarf binaries. And these measurements mean that the maximum mass of the neutron star must be at least around 2 times the solar mass. So whatever your equation of state is, it must be able to produce at least neutron stars of at least masses of 2 times the solar mass. And radius measurements of neutron stars are much more challenging, and so they have higher uncertainties, but there are already some results. And the most important source for these is cooling of the X-ray burst coming from neutron stars in a binary. And this can be measured and modeled, and these give you, well, radii around of between 10 and 15 kilometers. Some measurements claim even better uncertainty. But what is important is that more and better results are coming in all the time and are also expected in the near future. For example, this NICER experiment, which has already released some data, will improve the radius measurements, for example. But apart from isolated neutron stars, as you probably very well know, there are also neutron star mergers. And neutron star mergers are significant sources of gravitational radiation. And well, if you have a neutron star merger, you can measure both the gravitational wave signal and possibly the electromagnetic signal coming from the same effect, and they both constrain the microscopic properties of dense matter, or can be used to constrain their properties. And these kilonova events are likely the origin of short gamma ray bursts and the heaviest elements in the universe. And in this diagram, I saw schematically the evolution of a neutron star merger depending on the mass, well, as a function of time, and depending on the total mass of the binary system. So if the system is very high, like in this first case, well, there's the binary which inspires us for a long time, and at some point it will merge, and if the mass is very high, it will immediately collapse into a black hole. And in this case, the gravitational signal is very simple. There is an in-spiral phase, and then at some point there is just a merger, and then the signal dies out. But at intermediate masses, there is a little bit more complicated structure. So after the merger, you may get this so-called hypermassive or supermassive neutron star, which stays alive for some relatively short time, and only after that the system collapses into a black hole. And in this case, there is this intermediate phase of higher frequency signal after the merger, which carries imprint of the structure of the system. And at smaller masses, well, you still generate something like supermassive differentially rotating final state, but then you don't necessarily collapse into a black hole, at least not in the short time scale which you see in the simulations. Then later, when the rotation of the neutron star is slowed down at very long time scales, it may still collapse into a black hole. And in that case, in the neutron star, well, in the gravitational wave signal, you also see like after merger signal, but there is no point where it collapses into a black hole. And as you probably know, there was already one good neutron star merger event, which was where the gravitational wave was observed, as well as the electromagnetic signal. And there are also other candidates. And already this first event set some constraints on the or can be used to constrain QCD equation of state. I will discuss now how this happens. So from this event, one has been able to constrain this parameter, the so-called tidal deformability, which measures how strongly neutron stars deform in gravitational field. And well, in this event, what they measured was basically only the in-spiral signal. And the in-spiral signal which they saw was almost exactly consistent with just point-like objects in-spiraling towards each other. And so there was basically no deformation at all. So that's why this signal only gives an upper bound for this parameter. And well, this can be translated to a rough upper bound for the neutron star radius. So actually I'm showing here in this plot on the left bottom the probability distributions on the radius mass plane for the two neutron stars taking part in this merger event. And you see that the probability distribution dies off at, well, 13.5 kilometers. So that's roughly the upper bound for the neutron star radius set by this event. Well, there is also a lower bound, but the lower bound is not strict. It's the upper bound which sets constraint to the equation of state. And I will show explicitly what this now means for the equation of state. So this is pretty much the state of the art for the equation of state for QCD at exactly zero temperature. And well, this plot which I'm showing here, the log of pressure as a function of the log of energy density, this was obtained by studying interpolations between nuclear equation of state at low densities and perturbative QCD at high densities. And it's constrained by these measurements of the neutron star masses and also this LIGO constraint for the tidal deformability. And this requirement that the equation of state must be able to support neutron star masses of at least 2 times the solar mass excludes this Zion area in this band spanned by all possible equations of state. And then this additional constraint of requiring that the tidal deformability is below the bound or set by LIGO and LIGO-Virchow excludes this red area. So what we know is that the equation of state should lie in this green band. So there is still quite a bit of uncertainty in the region of intermediate densities. And the source of these uncertainties is, of course, that it's physics have strong coupling. We haven't been able to solve QCD in this region, and therefore it's natural to ask if holographic methods can be used to reduce these uncertainties further. And this takes me to the second topic of my talk. So modeling dense holographic quark matter, or modeling dense quark matter using gauge gravity duality. And now I don't seem to be able to go further. Oh, okay. I don't know why it got stuck. Anyways, before going on in the like models which I will be discussing, I will give a brief overview on what people have been doing earlier on. Like one of the first papers studying this, well, maybe not the first papers, but the ones which have been really trying to apply this for neutron star was this paper in 2016. And they used for quark matter the D3, D7 top-down model. So it's a super young Mills, but plus some probe fermions in a fundamental representation. And so they only used this top-down model for the quark matter part, and for the nuclear matter, they just used some standard effective field theory results from this paper. So actually what I'm showing here on the left is the equation of state, and these colorful curves are the equation of state from this nuclear theory paper. And this black curve is the equation of state from the D3, D7 model. And at some point, depending on which nuclear matter model you use, the pressures of the two models meet. And there you see that you say that this is the phase transition point from nuclear matter to quark matter. So at low densities, you use, well, for example, this intermediate equation of states here, and then you will say that this is the transition point, and then at higher densities you use the D3, D7. You say that this is your equation of state. And then using this equation of state in the TOV equations gives you this kind of mass radius relations for the neutron stars. And so all of these colorful curves on this right-hand plot are neutron stars which only contain nuclear matter. So they are just based on this effective field theory results. It's these black curves which also have a like quark matter cores described by holography. But as it turns out, all these neutron stars on these black branches are unstable. So, well, actually, because the nuclear to quark matter transition in this kind of setup is very strong, this makes the neutron stars with holographic quark matter core unstable. And well, this has been studied more. So the same authors studied varying the quark mass in the model. And so you obtain quark stars and hybrid stars. In particular, they obtained sizable deviations from this universal I love Q relations, which are these are various quantities which describe the properties of isolated neutron stars. And then the group at Southampton has been including the running of the quark mass and the possibility of color superconductivity in the D3, D7 and D2, D7 motivated systems. And they observe this possibility of an intermediate chiral symmetry breaking but deconfined phase. And with these modifications, they obtained even stiffer holographic equation of state, higher speed of sound, which actually makes it in principle easier to obtain like feasible holographic neutron stars. And indeed, they have obtained neutron stars where you actually do have stable quark matter cores. And well, this has been studied also in the Witten-Sakai-Tsukimoto, where actually it suggests there's also weaker transition or crossover from nuclear matter to quark matter is possible. And there have been other studies using Einstein-Maxwell dilaton system, and also quark stars have been studied in Witten-Sakai-Tsukimoto and in D46 models. Well, but in the rest of the talk, what I want to discuss mostly is to develop these approaches towards some more realistic models, holographic models for quark matter. And the model which I will be using is this, what we call the holographic V-QCD model. So this is a holographic bottom-up model for QCD in the Veneziana limit, which means that we take the number of flavors and number of colors large, giving this ratio NF over NC fixed. So the V here in this name comes from the Veneziana. So this is a bottom-up model. It's constructed by hand, but we are trying to follow principles from string theory as closely as possible. I will give you more details later. But anyways, it has lots of parameters. So it's an effective description of QCD. And in order to determine the values of the parameters, it's essential to compare the model carefully with QCD data. But I think that this model works surprisingly well, in particular in this region of dense QCD matter. I will show examples. And then going to a little bit more detail, the model is obtained through fusing two building blocks. And the first building block is the model for the gluon sector of the theory, for the model for pure Young-Mills theory, which is this improved holographic QCD model. It's defined in terms of a 5-dimensional dilaton gravity. And then the second building block is how you add a flavor sector, so quarks also in this business. So this is done by adding flavor and chiral symmetry breaking by these tachyonic brane actions. And in the Veneziana limit, you have full back reaction between these two sectors. And taking this Veneziana limit here then essentially defines the model. But I will show you a little bit more details here on this slide. So the model has two bulk scalars. So the first scalar is the lambda. It's actually lambda is the exponential of the usual dilaton field, and this is dual to the trace of S squared operator in QCD, and therefore it actually sources the soft coupling, in field theory. That's why we denote it by lambda. And then the other important field is the tachyon, or what we call the tachyon, which is a scalar field which is dual to the QQ bar operator. So this controls the chiral symmetry breaking in the theory. And the action has two terms corresponding to the two sectors. So the first term here is the improved holographic QCD action. So you have the Einstein term for the gravity and a kinetic term for the dilaton. Well, this 1 over lambda squared here is just because the lambda is the e exponential of the dilaton. And then there is a potential for the dilaton, which is at the moment it's just arbitrary, but I will discuss how to fix all these potentials in a moment. And then there is a second term, which is the description of the quark sector. So this is a DPI action, but because, well, we are back reacting, we are in a region where this action really cannot be derived strictly from string theory. And then in order to sort of parameterize our ignorance, we insert these potential functions for the kinetic terms of the tachyon and also in front of the gauge field, as far as in this sort of the tachyon potential term, which are also taken to be arbitrary. And this exponential tachyon behavior is what is motivated by the Zen kind of approach for brane decay. And so, as I said, this is an effective model for QCD. So we need to choose these potentials appearing here by comparing to QCD data. And well, there are lots of potentials, but well, they are quite strictly constrained. And in particular, these need to be quite simple, like monotonic functions, which with no special features, because if you put in special feature, you will very soon realize that you are in big trouble. You won't get anything physically reasonable. And they are constrained asymptotically by qualitative features of QCD, such as confinement and asymptotic freedom. And asymptotically, I mean at small values of lambda and large values of lambda. And then the remaining degrees of freedom need to be fitted to lattice data. And this is what we have been doing in particular in this paper. So we fitted some lattice data. So we computed some thermodynamic properties from the model just by using the standard dictionary. So you need to solve everything numerically by using the action which was on the previous slide. And so let me discuss the fits in a bit more detail. So what I'm showing here is the interaction measure in QCD at 0 chemical potential as a function of the temperature. And the red dots are lattice data from this paper, and these blue curves are various fits by using the holographic model. And well, as I said, there is lots of parameters, but as it turns out, this fit is sort of stiff. So that means that the result is relatively insensitive to the values of the parameters. And so in particular, you cannot fit any possible shape of these curves by using the model. It's a small miracle that you can fit, for example, the interaction measure so nicely, given the degree like freedom which you have in the model. I wasn't expecting before we did the fit that it would work so well. And another thing which we fitted is the baryon-Naube susceptibility, which measures, well, this is the first non-trivial cumulant of the equation of state when you go from 0 chemical potential to finite chemical potential. It's the second derivative of pressure with respect to the chemical potential. And you can also fit that nicely. So this means that you can describe the lattice data at small densities very nicely, for like the lattice data for QCD equation of state. And then what we did next is that we checked, we wanted to extrapolate the result to the region of large densities and small temperatures. And this is how it looks like. So this band which I'm showing on this equation of state plot is basically the same band which I showed earlier. So this gray is all possible. Gray region is spanned by all possible interpolations between known low and high density limits. And these blue and green curves are fits. Well, they are obtained from these different fits to the lattice data by extrapolating to 0 temperature. And what is nice is that our results for the equation of state, in particular at high densities, are in the band. So this is what we want. And at low densities, they go outside the band, but this is not a problem because at this point we are only modeling quark matter. So at low densities, we expect anyways to have a transition to nuclear matter. And actually, comparison with this like known nuclear equation of states suggests that there will be at some point a first order phase transition where you go from quark matter to nuclear matter here, because the curves are not on the pressure energy density plane are not intersecting. So this happens for first order phase transition. And also the fact that they are clearly separated means that the first order phase transition must be quite strong. So this is actually the picture is quite similar to the simplest D3D7 model, but it's a little bit in contrast with what people have been obtaining in the Witten-Sakai-Tsukimoto model, where the transition between nuclear and quark matter is smoother. But okay, so the missing ingredient here then is to plug in also the nuclear matter, and this will be the topic of the next part of the talk. But before going to nuclear matter, I will do a small digression, because now that you have constructed the model, you can also look at more complicated observables than just the equation of state. And this is, in particular, we have checked transport properties just for the quark matter phase. This is relevant because, well, bulk viscosity is probably relevant for neutron star merger dynamics. And all this viscosity is also damp these instabilities in spinning neutron stars. So measurements of the spinning neutron stars give constraints to viscosities. And the conductivities are relevant for neutron star coolings and equilibration after neutron star mergers. But actually, the transport, obtaining predictions for transport from QCD is very challenging, because, well, already for the equation of state for QCD, there is a large error bars at the moment, but for transport, the situation is much worse. Well, basically, the only available first principle results is leading order perturbative QCD analysis in the unpaired phase. And what we did in this paper was that we studied this, carried out a strong coupling holographic analysis, both using these D3, D7 and V-QCD models. I will show you some of the results that we got.
Sorry, Matti, can I ask you a question? Sorry to interrupt.
Yeah, sure.
It's David here. So I agree that viscosity may play a role in these instabilities in neutron stars, but I would have said it's not QCD, the viscosity that's relevant is not QCD viscosity, because the gradients are very small on a QCD scale.
Right. Yeah, that's true. Yeah, that was one of the comments which I also wanted to make. Thanks for pointing it out. Right. So, I mean, you can see from our results here for the viscosities. So these are for the quark matter phase. On the left-hand side, I saw the log of the shear viscosity versus log of the T for two different values of the chemical potential, quark chemical potential actually. And on the right-hand side, I saw the same plot but for the bulk viscosity. And these green bands so the perturbative QCD result where it's available, which is the case for shear viscosity. And these different curves here are for the D3D and D3D7 model, and for V-QCD model for slightly different parameters. So here for the shear viscosity, we have quite, well, there is large deviation for the perturbative results for either of the holographic model. And for the bulk viscosity, there is actually even the D3, D7 and the V-QCD results are different. This is basically due to the fact that in this D3, D7 model, we didn't take into account the back reaction of the flavor brains to the colors, whereas in this V-QCD is included. So we think that the most reliable result here is the V-QCD result. And yeah, and as you already pointed out, this is only the QCD contribution to these viscosities. And so there are other contributions which are significant, from electrons to both conductivities, and then in particular from weak interactions to the bulk viscosity, which is that contribution is expected to be leading this ideal QCD contribution by orders of magnitude. So in this sense, this is not important, but anyways, this is the basic QCD result, like basically the first possibly reliable computation. But anyways, this was sort of a digression. I think now I want to go back to the equation of state again, but discuss now also the inclusion of nuclear matter. And this nuclear matter has been studied a lot in the holographic literature, in particular in the connection of the Witten-Sakai-Sugimoto model. And it's basically known how to put baryons in the bulk. You need to consider these solitonic instanton configurations of gauge fields. And yeah, this has been studied in Witten-Sakai-Tsukimoto model a lot, and using some very simple approach, you get some rough model for physics of QCD at finite density. And there are complications. As it turns out, the baryonic phase is actually not a liquid, but like nuclear, instead of liquid nuclear matter, you have these solid-on crystals with non-trivial transitions. I even had recently a paper on this. And you can also have this quarkionic phase where you have a sort of mixture of quarks and baryonic degrees of freedom. And well, this kind of solitons have been also constructed in hard wall models, and there is also ongoing work in constructing this in V-QCD, but this is not what I will be talking about today. So it's too early to talk about this. But I will be actually doing something completely or much simpler, which doesn't really take into account this soliton structure explicitly. And this is the motivation for this is because doing these solitons at neutron star core densities is very hard. At low densities, you can work with separated instantons and maybe two-body interactions between them. But when you go to high densities, you will have many body interactions between these solitons, and they will start overlapping. And then there is also the problem that actually the phase where you are is a crystal instead of a fluid at large NC. And we try to just use a simple approximation scheme where we, instead of solitons, we just study a homogeneous field for the nuclear matter, which is perhaps a reasonable approximation at high densities where the nucleons are very close together. And so what we do take is that for the non-abelian gauge fields, well, we restrict to NF equals 2, so we have only SU2 flavor symmetry, and we take the non-abelian gauge fields basically to be of this form where sigma I are the Pauli matrices, and this HR is the holographic nuclear matter field. And this has been studied in the literature in the context of Witten-Sakai-Tsukimoto model, where people actually maybe didn't find that nice results. But as it turned, we try it in V-QCD, and I think we are getting much nicer results, which I will discuss in a moment. But there is, when you try to do this, there is an immediate problem which you need to solve first. But this also appears in Witten-Sakai-Tsukimoto. So if you assume that with this ansatz that this H function is smooth, as it turns out, you don't get any baryons. So your baryon number is just 0. And so how do you avoid this? Well, you can think that this homogeneous field should somehow come out from smearing the individual instantons. So what you can do is that to get motivation is that you just smear the known PPST soliton solution, which is actually the solution which you have in the extreme strong coupling limit in Witten-Sakai-Tsukimoto. And if you do it in singular Landau gauge, you just smear over all spatial directions. You get this kind of function, which I plot here in this right-hand plot. It sort of looks like a step function. And motivated by this, well, I think it's reasonable to introduce a discontinuity to this field HR. So what we plug in is something like this, where there is a non-trivial discontinuity at some point in the bulk. And you can imagine that this discontinuity somehow arises from these singular soliton centers after smearing them out. And this discontinuity sources non-zero baryon charge. And okay, I'm skipping lots of details, but you need to plug in this ansatz in your DPI action and develop it and minimize with respect to the location of the discontinuity and its size at fixed baryon number. But basically what you get is this kind of phase diagram, again, as a function of temperature and chemical potential. So here the green region is the confined phase, and the red region is the deconfined phase. And this blue region is actually where this nuclear matter now appears. So in this region, the confined vacuum shows the instability towards forming this nuclear matter condensate.
Sorry, Matti, one more question. If I understand correctly, you're using the DBI action for a non-abelian configuration, or is that right?
Yes.
So what prescription do you use for the non-abelian DBI?
Well, it doesn't matter because actually, yeah, I skipped all details, but we are only treating these solitons as probe. So we are developing the solitons to leading non-trivial order in this non-abelian gauge fields. And at leading non-trivial order, there is no ambiguity in the action. I mean, in principle, you could try to look at higher order corrections or more like DPI, like setup, but we haven't. I mean, anyways, we are doing rather a rough approximation with taking these homogeneous fields. I think this is the reasonable first approximation which you should try.
No, I was just wondering if you're using this symmetrized trace prescription.
Yeah, but I mean, in principle, yes, but it really doesn't matter at this level of approximation. All the possible prescription gives just the same result. Because it's only when you go to higher order terms in the non-abelian gauge field strength tensor. We are only working at the level of sort of f squared.
Okay. So just trace of f squared. Okay, thanks.
Yeah.
Thanks.
Right. But okay, so now you have in principle constructed the model, and you can already extract an equation of states, say here, for low temperatures and high densities, and start studying the new neutron stars. But there is actually, we plug in one more ingredient, because as it turns out, or as it's quite obvious from the approach that we are doing with this homogeneous field, this description is not reliable at low densities. Because, well, at low densities, you know that you really should have individual baryons. But this is not a problem, because at low densities, we already know what the equation of state should be, pretty much. So at low densities, we just take some of these traditional nuclear theory models instead. And then what we do is that we match these nuclear models with V-QCD at some intermediate densities. So here on this plot, I show an example of such a matched equation of state. It's this green curve. Here I'm using this APR equation of state for the nuclear matter. So this gray curve is the pure APR equation of state, which I'm using at low densities up to this point, which is actually something like 1.6 times the nuclear saturation density. And at higher densities, I just use the V-QCD model. So this part of the phase diagram is coming from the nuclear matter model, and then the rest is coming from the holographic model. So in particular, the dense part of the nuclear matter is coming from holography, and the phase transition between nuclear matter and quark matter is all described only by using the holographic model, and also the quark matter phase is described by holography. And okay, so this green curve is an example of this kind of equation of state, but we have studied for this a family of equation of state which you can get by varying all model parameters, both in this nuclear matter side and in the V-QCD model. And what you span is this red band. So the main result is that, also taking into account constraints from astrophysical observations like the neutron star mass and the LIGO work bound for data deformability. So we claim that if the holographic model is correct, then the equation of state should be in this red band. And if you don't use any constraints from holography, you only get this light blue band. So the band, using holography, the band is significantly reduced. And then going maybe, if I have time, in a little bit more detail. Yeah, so let me So the speed of here I saw the speed of sound squared as a function of the number density. So here it's the, well, this is actually the nuclear model part. Then there is holographic nuclear matter here. Then there is a phase transition to quark matter, and at high densities you have quark matter. And well, there are some different curves here corresponding to different model parameters. I don't show all the different models here, but there is relatively mild dependence on model parameters. This like the difference between these two curves almost already exhausts all possibilities. But the point is that this has been, of course, studied by using other methods, and in particular, there is this functional renormalization group method, which is sort of another sort of non-perturbative approach to equation of state. And interestingly, what these guys find is very similar to what you have here. So here I saw the functional renormalization group method for the, well, you should look at this plot. This is the speed of sound as a function of, say, number density. And they are using different units, but if you would overlap it with our plot, it would be something like this. So it's sort of qualitatively quite similar to what we get. And then there is another plot where people consider functional renormalization group in the quark matter phase. And in their case, it's this curve, which is coming from the functional renormalization group method. And also that seems to match with what we have for the quark matter. So it's interestingly close. But anyways, I should hurry and go to the last topic, which is applying these results to neutron stars. The first sort of obvious application is that you have constructed this equation of state. You just plug them in the TOV equations and you get mass radius relations for neutron stars. And here I'm showing the mass radius relations which we are obtaining. So this green curve is for an example. Actually, it's the same example of equation of state which I showed in one of the previous slides. So APR plus V-QCD. And so if this equation of state is correct, all the neutron star masses and radii should lie on this curve. But if you then vary again all model parameters, you span this red area. And this is again, this red area is significantly reduced compared to what you get without holography. And we obtain that, well, the holographic construction prefers quite large radii of the neutron stars. And okay, I should also point out that in this construction, all these neutron stars only, which are stable, they only have nuclear matter. So the first order phase transition to quark matter, in the same way as in the T3D7 model, makes the quark matter cores unstable. And then in a recent paper, we studied also rapidly spinning holographic neutron stars. And this is motivated by this recent observation from LIGO Virgo, where they observed this highly asymmetric merger of a 23 solar mass object, which was certainly a black hole, with a 2.6 solar mass companion. And this 2.6 solar masses falls in the gap where you really shouldn't be observing black holes or neutron stars. And it's not known if it's a black hole or a neutron star. So we tested with our equation of state. Now, maybe I won't go in too much detail of this plot, but the range, the region with stable masses and radii of spinning neutron star is this region between the two red and blue curves. So this was obtained, well, this is an example of an equation of state coming from the holographic model. And if we assume that the neutron star spins rapidly, then we can easily get to the range of masses which was measured in this event measured by LIGO and Virgo. However, this requires a very fast rotation. So the rotation frequency of the neutron star must be larger than 1 kilohertz. This is actually faster than in any observed like millisecond pulsar so far. But okay, let me go to another topic. We have also used this equation of state in simulations of neutron star mergers. So we did 4-dimensional gravity simulations of neutron star merger by using publicly available tools and used as an input an equation of state coming from the holographic model. And now I think I have time to show you and some animations from these simulations. And if I switch into now you should be seeing the simulation. So this is actually from a simulation of a merger of two neutron stars having 1.5 times the solar mass each. And here actually I should point out that part of what I'm plotting is the logarithm of the energy density, and part of the space was cut out of the simulation just to see better what is happening in the middle. And okay, so this is the in-spiral phase, but what you see at some point is that the two neutron stars merge, and since actually what happens is that this is at quite high, or this is at a relatively high mass of the total system, so the system immediately after the merger collapses into a black hole, leaving behind some L-torus. And maybe I have time to show also another video. But I think I need to share it also. Where is the Zoom? Okay, so now you should be seeing another video where I show the log of the energy density in two different planes from the simulation of actually. Now the neutron stars have masses of 1.4 solar mass each. So the masses are a little bit smaller. And what happens in this case actually is that the system doesn't collapse immediately into a black hole, but it forms this differentially rotating hypermassive neutron star, which stays alive for a few milliseconds. And after a few milliseconds, the differential rotation is attenuated enough, so and then it collapses into a black hole. And so what you see below is the generated gravitational wave signal. Now I should go back to the And one of the main results which we can extract from the simulations is this power spectral density. So the power spectral density characterizes the properties of the outgoing gravitational wave signal. So it's defined like this. So you extract the amplitude of different polarization of the gravitational wave far away from the source, take a Fourier transform, and then this average over the different polarizations. And this is, I'm showing here, so it's basically a Fourier transform, certainly in a Fourier transform normalized in a certain way from the gravitational wave signal. And I'm showing here the simulation results from one of our simulations. Actually, this is at 1.3 solar mass, equal mass merger. And so this is the power spectral density as a function of the frequency. At the low frequencies, this part of the signal is coming from the in-spiral of the stars, but this higher frequency part is coming from the after merger dynamics, and this is the more interesting part for us because this carries the imprint of the equation of state. And the main feature which we saw is that, well, there is this peak in the spectrum, this F2 peak. Well, it turns out that this holographic equation of state predicts relatively low frequencies for the strongest peak. This is one of our main results. And I should also point out that this gray curve here is the sensitivity curve for the LIGO-Virgo experiment. It's the current sensitivity curve. And actually, this event is, the simulated event is normalized in such a way that it's assumed to happen at the same distance as this good event, which they already observed, this GW170817 happened. So if this event would happen now, well, with this kind of parameters, you should be able to already disentangle this F2 peak. Well, they missed this in the first event because at that point, the sensitivity of the experiment was a bit lower. Okay, but let me go to the last point, which I want to discuss, a little bit different thing. So, well, I didn't tell you, but well, in the simulation which we carried out here, we really didn't have a proper temperature dependence in the equation of state. We just used the holographic equation of state at 0 temperature, and then the temperature dependent was added in a rather naive way. But for state-of-the-art simulations, you really need to establish a proper physically reasonable temperature dependence to your equation of state. And well, and this is what we are trying to do at the moment, because this is really required for the state-of-the-art simulations. However, this is very tricky. It's very tricky to get this temperature dependence from the holographic model, in particular in the nuclear matter phase. The quark matter phase is actually not a problem. This is basically due to the fact that the pressure would come from like these hadron gas contributions, which are 1/NC in the large NC limit, and these are not captured in holography. So instead of trying to do this holography, we first try to just use some very simple model for like gas of protons and neutrons, using some van der Waals and mean field interactions, which are adjusted in such a way that you get a match with the holographic model at 0 temperature. And then this model extrapolates the equation of state at finite temperatures. And this, well, this is in progress. I'm showing here, well, a preliminary plot for the pressure as a function of the baryon number density in units of the saturation density and as a function of the temperature. And this feature, which you can see in this plot, is the nuclear to quark matter transition. And as it seems, what we are getting is that when you heat up or when you go to higher temperatures, yeah, so this flat region here is a mixed phase between nuclear and quark matter. And when you heat up the system, the mixed phase goes away, and it turns out that you basically get a critical point at some point in the phase diagram. It's at around 100 MeV in temperature. This is actually maybe not surprising because it's very close to the point where you get a critical point in this Einstein-Maxwell-Dilaton extrapolations of lattice data. This work by the Colorado group and also other people later. But anyways, this was everything I wanted to say, so I will just conclude. So the main points were that gauge gravity duality is useful for studying dense QCD compared with other approaches, such as the lattice data and effective field theory. And we used V-QCD with some simple approximations, and many details worked really well. Well, first, we were able to get a precise fit of lattice thermodynamics at small densities. And then when we extrapolated from small densities to higher densities, the extrapolated equation of state seemed to work very nicely. And we were also able to model nuclear matter in the model. So we were able to establish the simultaneous modeling of nuclear and quark matter, and in particular, the phase transition from nuclear to quark matter. And yeah, I didn't talk that much about the stiff equation of state, but one point was that we clearly violated the sort of the conformal value or the conformal so-called bound of the speed of sound. So our speed of sound was much higher than the conformal value, in particular in the nuclear matter phase. And this is important because it's required for the equation of state really be feasible, because otherwise you cannot get high enough masses for your neutron stars. And we computed predictions for various things, equation of state for cold matter, we transporting quark matter phase, and then basic properties of static and spinning neutron stars, and also gravitational wave spectrum in neutron star mergers. And there is much ongoing work, so more results will be coming in near future. Thank you.
Thank you very much, Matti. I'm sure there are some questions.
I have a question too, surprisingly. So could you say a couple of words or more words about this mean field model that you use to include finite temperature effects? I didn't understand exactly, not the technical details, but what you're doing.
Yeah, it's okay. So I mean, there are two ingredients. First, there is basically van der Waals, which means that we are just taking a gas of neutrons and protons, and we are saying that they are like solid balls. So we just exclude a volume of, like a constant volume of for both protons and neutrons. And this already plugging this in gives you something which is quite close to the holographic equation of state with it properly adjust volume. So this gives you something which is relatively close, but then you sort of need to fine tune it to really get a perfect match with the holographic model at zero temperature. And we do this, so we add a field, this sort of mean field, very simple mean field approach, like you're almost naive. You just take an sort of a potential as a function of number density, which you add to the chemical potential of the nucleons. And if you adjust this potential in a reasonable way, then it's gives you an exact match. And you assume that this potential only depends on the number density, which I think is a physically reasonable assumption. So there is no temperature dependence in this potential term.
But these balls that you use to model the protons and the neutrons and this mean field, are they, is that a model in the gauge theory side or on the holographic side, on the gravity side?
Well, I'm not sure if it's really even gauge theory, but it's
is it a four-dimensional?
It's four-dimensional gas model.
Okay.
Yeah.
And why wouldn't you just use effective field theory or QCD, chiral perturbation theory?
Right. You could try, but I mean, the point is that we really want to get the model in this region of very high densities, well above the saturation density. You could use effective field theory, but it's known that the effective field theory, like chiral perturbation expansion, no longer converges at such high densities. So I think that's why it's like best to just stick to the simplest approximation, because I mean we don't know really how to do the temperature dependence in this region, but like no one else does know that either. So
I see. So basically you're providing a different four-dimensional approximation, hoping that it does a better job when you go to high density than chiral perturbation theory would do.
Like you could try to do something more sophisticated, but it's known that the more sophisticated methods are not reliable either.
Yeah.
So
I'm just, I see.
Yeah, and this model has some parameters. You can try it like varying the size of the excluded volume and still fit when I mean, because there are two components. There are the size of the excluded volume, and then there is the potential, and you can sort of vary the other, and so that the result at zero temperature like you chase both of them so that the result at 0 temperature stays unchanged. And then maybe this we can see how this affects the extrapolation, and we get some sort of feeling on how large the uncertainties are in the construction. Of course, you cannot do anything systematic. But
Thank you.
yeah, anyways, it seems to give something which looks reasonable. It compares nicely also with the quark matter result, because the quark matter result is directly coming from the holographic model.
Are there more questions? I have a question which might be just coming to my mind because David is here, because you had he had a paper with Rob Myers on phase transitions at finite baryon density or finite chemical potential. I remember, and correct me if I misremember or misrepresent anything, but there was some so that at the time there was I think you discussed the transition between Minkowski embeddings and black hole embeddings, and then in one ensemble with the chemical potential fixed, I believe it turned out to be it looked like there was a transition between those two, but then once you went to the canonical ensemble, you had the fix the charge density, and then you saw there was a transition between two black hole embeddings instead. I'm just, since this is at least inspired, Matti, by such constructions, D-brain constructions, to a level which you'd have to tell me how much it is like reflected in here, these constructions. But you said you're using the trace of f squared, right? So that leads me to believe that similar structures should show up here as in those constructions. So I'm just wondering about, have you looked at the chemical potential version of this diagram?
I'm not too familiar with the details in D3, D7. I guess there are much better experts in the audience, but I can tell you roughly what we have, like in this phase diagram. I mean, I didn't even mention what the different geometries were during the talk, but this deconfined thread phase, this is a black hole phase. So in this phase, you have a black hole geometry. That's why actually in this phase you get this non-trivial thermodynamics and equation of state. And then in this green region, the geometry, it's sort of well, it's not really an Minkowski embedding, but I mean, there is no black hole. It's this what we call the thermal gas background. Instead, the geometry is such that it ends at some sort of it's this good kind of infrared singularity. And it's because of this, the absence of the black hole, that the thermodynamics is so simple, actually. So there is actually, the geometry is independent of temperature. And actually it's also independent of the chemical potential. That's why, yeah, the thermodynamics is so like trivial. In particular, this phase transition line here is just vertical. So the only non-trivial dependence on chemical potential is then in this region where you actually start having this condensation of this nuclear matter.
And you can reach each point in this phase diagram, is that right?
Yes.
As opposed to, you're jumping from one point to the other.
Right. Yeah, I mean, yes. I mean, maybe it would be more physical to draw this as a function of charge rather than chemical potential, and then because this part of the phase diagram is sort of trivial. This is just empty space. There is no matter at all. And if you draw this as a function of the charge, then this the whole green area is just strings to a line here at zero density.
Okay, thanks. Are there other questions? Well, okay, then I would like to thank you again, Matti. We stick around after the official talk, so I'll end the recording. So thank you again.